All right, so welcome to the first talk of the afternoon session. So it's the first of 4 lectures by Professor Suresh Nayak, and he's going to talk about residues and trace maps in Grothendieck duality.
Yeah. Okay, thanks. So I thank the organizers for inviting me here to give a talk, and also for arranging the talk in the afternoon so that most people can fall asleep very comfortably. Okay, so here's a tentative plan. Tentative plan is I'll have 4 parts. So first is sort of main duality statements. Then, so this will be over pretty fast. Then proof outline of Poincaré duality. Well, in a special case, so that will give you a flavor of what's happening. Then main statements of Grothendieck duality. Main statements and properties, and the last one will be residues and traces. So most of it is stuff which was done more than half a century ago, but certain technical points needed clarifications, and so it's towards the end I will get to what I really wanted to talk about. Since this is a conference on dualities in algebra and topology, I thought this is formally somewhat similar to the statement here. I'll also talk about this a little bit. Okay, so I'll start with the first part. So let me first mention Serre duality, since I think this is the context in which many of the constructions arose, especially the definition of derived category and then formulation of Verdier and Grothendieck duality. They all are related to this one. So let's start with X, smooth projective variety over an algebraically closed field if you want complex numbers, or doesn't matter. So just take this, and E, a locally free sheaf. Then Serre duality. I will not state the version which was given in the morning, the what is it? The Serre functor business. So here's the one which is closer to the original statement. So then we want to say that HI, okay, did I mention dimension of dimension n? Then HIX E dual is, so there's a canonical or natural isomorphism, Hn minus I X. Yeah. Okay. So this is classical Serre duality. And one should note that one can easily see that this is in fact isomorphic to the following group X and I over OX modules of E and omega n x. So then this gets generalized. So let's generalize. That's a form in which was somewhat mentioned in the morning. So consider. So instead of looking at E to be any locally free sheaf, we'll look at E belongs to D plus of quasi-coherent sheaves on X. I want double brackets. Okay, let me have it. So I'll take any complex, bounded below complex of quasi-coherent sheaves. So then, so this above isomorphism can be viewed as H minus I applied to, rather I should say that there's a more general statement which implies this one. So is, okay, let's just continue like this. So applied to, so I'll just write the derived version, which is R gamma E. But then I want, sorry, I want one more thing here. I want to dualize it. So R hom, but this hom is really not so serious because it's over a field K. And so it's just hom, I mean, in some sense. So this is a complex. This complex is basically, okay, sorry, E dot. Okay, this is just to highlight that I'm looking at it as a complex. So I'm looking at a complex here. So replace it by its injective resolution, apply gamma, so that will give me a complex. Apply gamma global section functor, that will give me a complex of vector spaces, dualize this. Then in the derived category, this is isomorphic to, so this side is again obtained by applying H minus I. One should view it as being obtained from a more general result. And the general result is, this is R hom. So let me just put R hom dot. And then I have dot. Yeah. Okay. So D plus is bounded below complexes of quasi-coherent sheaves. Yeah, they're going rightwards. So injective resolutions in that direction. So you can, if you want, you can think of EI is equal to 0 or I less than less. I mean, take the derived category formed by derived category of complexes in which this property is true. That's equivalent to the derived category of, okay, no, let me stick to this one right now. Okay, and this is R hom dot. This is being computed as R hom dot is over OX modules. And so this is the statement. So this isomorphism is in the derived category of complexes over K of vector spaces over K. I mean, both these are complexes of vector spaces over K. And that's what we are computing. I mean, we are taking hom but the output is just a vector space. And this is related.
Sorry, Suresh. The HOM is a sheaf HOM or the regular global sections?
It's a group HOM. That's why I said. So this
okay,
is,
okay. Sorry,
thank
you. Yes.
Just HOM of OX modules, but the output is vector space.
Fine. Thank you. Yes.
Or one could also, a closely related statement is the following, and that is HOM in the derived category of K. Again, so maybe I need a name for this. So, okay, let me just call it DK. So this is, I'll call it DK. And now in DK of I'm saying or, but actually, let me not put or here. Let me, for the time being, put thus. And this is HOM X. And this is E dot. You can, in fact, though it's not very impressive sounding, but you can, in fact, replace K by any complex of vector spaces. Yeah. And here you can replace this by V dot tensor with omega n x n. So stated this way, it is an adjointness statement. So what we are saying is that the functor, which is sending E dot to R gamma x comma E dot. So this functor is, has a right adjoint, and that is given by the functor which is sending V dot to V dot tensor with omega n. Maybe I'll just state that. Yeah, oh, sorry, I forgot to mention this statement is more general because if you apply H minus I here, this is a dual, so, and this is exact, so this will just give you HI. And HI of this is HIXE. And then you're dualizing, so that's a dual. So that is the left-hand side. And if you apply H minus I to this, there's an N here, so that N, you can bring it out, and that will become HN minus I. And then it's just X N minus I, E omega n. It is more general. Yeah, it is because I am allowing any, this is anything in any complex here. This was just for locally free sheaves. Here it's any complex. Yeah, that's what I'm saying. So think of E as a complex. Then that's a special case of this. Does Serre duality imply this? No. Yeah, no, it's not so obvious. No, even for, projective, did I say? Okay, if it's projective, still it requires some work. It's not completely, okay. Will Serre duality immediately give? Yeah, maybe you can do something and, I don't know. I'm not, so then basically you'll have to look into how Serre duality was proved. Formally it's not so immediate that this implies, Serre duality implies this. So, if you can look into the proof of it and then maybe you can mimic the proof, and I don't know, that can say something, but formally. Yeah. So you have to set up the map, but for that you have to again work in the derived category and do everything. So what this means is that if you look at, I mean, I'm just repeating whatever is said there. So look at the functor f from the derived category of, so I called it x, huh? Okay. I should have called it, okay, here it doesn't matter because I'm just computing HOM. I should be
one question.
Yeah.
That notation R hom OX, you mean we are landing in the derived category of coherent sheaves, right?
No, R hom just means that you take, okay, one way is you take the injective resolution of the second term and look at hom dot, meaning complex hom of this complex into the injective resolution of this.
Yeah, so
that will be a complex of abelian groups, complex of
sheaves.
K vector spaces. No, not sheaves. This is not, I'm not computing sheaf hom. I'm just looking at hom.
Okay.
Yeah, in each index, it's just a hom. And hom means the output is just a, I mean, abelian group, but more generally, you can think of it as a K vector space. It's a K vector space in this case. So it's a complex of K vector spaces. Yeah, there will be a similar statement for sheaf hom, but for that, the two sides will live on different spaces. So you'll have to put some RF lower stars there.
Question. This is a statement not in the derived category of coherent sheaves, but a statement in vector
No,
spaces.
this is in the derived category of complexes of vector space over K.
Yeah, yeah. So,
there is a sheafified Grothendieck duality. That's a local version, and that will be a different statement.
Yeah. Okay. Okay.
So if you look at, so this is ad hoc notation. No, I have used that notation there. So if you look at this, and this one, I think I didn't create any notation, or did I? Derived category of, okay, I have this. Okay. Sorry, let's see. And if you look at G, this side is sending V dot to V dot tensored with. Okay, so here, I hope this is okay. I mean, this is a sheaf, this is a vector space, so you have to adjust, I mean, you have to define it appropriately. So at every open set, every section, you just tensor it with K. So that's what it means. So then these are adjoints. I'm not giving the full complete statement in the sense that these are actually triangulated functors and the adjointness is compatible with triangulation and with the shifts and such things. It's an adjoint pair. Okay, so now let me. Grothendieck duality is much more than that, but this is a flavor of how things generalize. So now let me go to the much more general statement of Grothendieck duality. And again, this will not be the most general statement, but for the purposes of these lectures, that will do. So again, you take a finite type map. And we need a technical Hausdorffness condition called separated. Of Noetherian schemes. Then the statement is that RF lower star, and this is a functor from, okay. Again, as I said, this is not the most general statement, so I will put more assumptions than what you will find in some of the papers on this. So right now we'll just start with this one. In fact, the plus is not needed. But okay, let me have it for the time being as a right adjoint. And we'll call it F cross. So this is in the reverse direction. So I'll just call it F cross. And what that means is, again, it's the same statement, same kind of statement. Okay, so let me just state it here. B plus Q co of Y, RF lower star F into G dot is isomorphic to HOM D plus quasi-coherent over X of F dot and then F cross G dot. This is actually not the, as I will soon point out, this is not really the main construction, but this is the starting point. So what we'll do is, assuming this statement later on, we'll show that and more and a bit more. So I'll say next time. We'll show that if F is smooth, let's say proper, and smooth, so I need both assumptions of relative dimension n. I won't go through the definitions of some of these terms, but proper is the analog of proper maps from locally compact spaces, but here it means universally closed map. And so it's a closed map, but under base change also it remains closed. Smooth of relative dimension n, well, it's a flat map. Fibers are smooth of dimension n, and okay, I won't go around defining this. So this is a generalization of having a, instead of, if Y is a point, then it's just saying that X is a smooth variety. And instead of projective, we have just made it compact variety. If it's over complex numbers, or proper variety, proper smooth variety. Then answered with omega n X over Y, and this is over OX. So pull back your complexes and then twist them by omega n. So that generalizes this one here, because when Y is a point, when Y is spec K, then F lower star is nothing but global sections functor. F lower star is the global sections functor when Y is a point. And so then that is exactly generalizing this statement here. So that's a relative version of that. But note the assumptions, proper and smooth. I need both the assumptions to actually recover that statement. Okay, I'll put some bullet points here. So this is the first remark concerning this construction. Second remark concerning this construction is that this construction here, the right adjoint, however, is not the correct object to look at in some sense, because it's not local in nature. So, for example, if I have an open immersion like this, then and then if you so take the same map, and what I want to do is I want to understand what is f cross g dot. I want to understand what is f cross g dot. It's a complex on x, and I want to get an explicit version of it. So the natural thing would be to restrict it to an open set and then try to understand what it looks like. But how do you understand what it would be on an open set? So you would like to, I mean, one possibility is you take the cross for the composite map, but it turns out that is not what you will get. So I cross is not isomorphic to I star, the inverse image. I inverse, which is I star in the, not I inverse, sorry, I star is, yeah, that's the same thing, okay. We'll put I star here, restriction. And so what that means is that if you look at f cross g dot and you want to know what it is on an open set U, you can certainly say that this is I star f cross g dot. So I just replace the restriction map by putting a star here. That's all I've done. Sorry, if the star and the cross look similar, so maybe I'll add some more lines here. So this is a restriction, but this is the right adjoint. And the right adjoint to the inclusion map is somewhat, I'm claiming, I'm going to now say that it's somewhat weird. So it's not what you would expect. And so this is not going to be isomorphic to I cross f cross g dot, which is for abstract reasons or other trivial reasons, because composition of adjoints is adjoints. So that will be fi cross, which is basically f restricted to u cross g dot. So what we are trying to say is that if you would be interested in computing f cross g dot on restricted to u, that will not really look like f restricted to u cross g dot. And that makes it a problem in the sense that, okay, I don't know whether that's a problem, but what that means is that, for example, statements like this with generalized Serre duality may not hold if you drop, for example, the properness assumption. If you try to go to an open set, you cannot expect this kind of statement. That statement is lost. For example, even for f is equal to identity map, you can see that they're not going to be equal. Local on y, meaning no. Oh, yeah. F cross behaves well. Yeah. Y can be assumed. If you want, you can assume y to be a point, but you are still, then you are in trouble because there's nothing to localize further. Yes, you can assume y to be affine. For example, assume y to be a point. Then there's nothing to localize here. So you still have this. So if you take a variety, which is not proper, but let's say it's smooth, it's not immediately, in fact, it's not true that you'll get something like this. So what we'll do is we'll later construct a more localizable alternative to f cross, and that will be called as f shriek. F shriek will be equal to F cross when F is proper. So then it is exactly the right adjoint to lower star. But when it is not proper, it will give you something else. And that something else again can be guessed by saying that if I is open, then I shriek will be equal to the restriction map. There when I is open immersion. And so I mentioned traces and residues. So when F is proper, there's a co-unit map. Just coming from the adjunction. So this is called as a trace map. And we will show that it's related to residues also. So for example, if X and Y are both spectra of fields, and it's a finite map, then let's say finite separable map, then in fact, this trace map will be closely related to the usual trace of fields. Okay, so that's a thing. And then the third part in this part one is Verdier duality. That's the fourth lecture, yeah. Though I think I'm going a bit slow, but it's okay. So Verdier duality. So Fx to y, continuous map of locally compact Hausdorff spaces. Often we'll assume it's, in fact, if you want, we can assume it's paracompact also, especially if it's a manifold, that's automatic. Having one technical condition called finite cohomological dimension. Which I'll explain later. It will be defined later. So basically, it means that cohomology with compact support vanishes after a certain number. So, for example, manifolds will satisfy this kind of condition. But this is much more general, and so that's the point, which is happening in Grothendieck duality also, that we are interested in having a duality statement for so-called singular spaces, spaces which don't look like manifolds or which are not smooth, which have lots of singularities, which have a mixture of components of different dimensions. So everything is allowed, and these are so this is the only general hypothesis. This is the only technical condition. In fact, again, this is not the most general condition. But for these lectures, we will work with this one. And for coefficients, I will use K, an Noetherian commutative ring. So when I sketch a proof, I will sketch the proof for fields, and then you have to adjust it or adapt it accordingly for other rings. Then statement is that, okay, so there's something called F lower Schrick. It's a slight modification of F lower star. F lower star is sections, push down of sections. So this is a direct image. So given a sheaf, so I forgot to say, I mean, I assume everybody's, or that's a prerequisite for my talks, is one understands what some of these terms are. So F lower star, for example, given a sheaf here, it will produce a sheaf here whose sections over any open set are obtained by just simply transporting the sections over the inverse image open set. So that is what F lower star is. F lower Schrick is a modification of that, where we have sections with compact support. So then I'll define F lower Schrick shortly, but let me first complete the sentence. So RF lower star, D plus of KX modules. Let's just say KX mod. So these are sheaves of, okay, abelian groups, but not more than that, sheaves of K modules. Sheaves whose sections over any open set is a K module. And then this is D plus of KY modules. And this has a right adjoint. And we'll call it F upper Schrick. And so what that means is Hom, again, similar statement, so D plus KX mod of, no, sorry, this has to be KY. And RF lower star, RF lower Schrick, F, G is isomorphic to no, there is something here. Yeah, that is has a right. Sorry. So this is isomorphic to F dot. Yes. In the next lecture, I will explain why, how this can be viewed as a generalization of Poincaré duality. But for the time being, okay, so first let me complete this sentence here. So where F lower Schrick is defined for any sheaf F assigns the sheaf, this is on Y, V goes to those sections S belonging to F of F inverse V. So if it was F lower star direct image, then I would have stopped here. I would have just looked at sections over the inverse image open set. But this is lower Schrick, so these are sections with compact support. So support of S Y is proper. One has to actually check that this is a sheaf. A priori, it's only a pre-sheaf. But the fact that properness is something that can be verified locally on the base, that needs a little bit of proof, but it's not difficult. That can be then used to say that this in fact is your sheaf. So let me just quickly mention why this is, what this is doing. For example, if capital Y is a point, this is just giving you global sections with compact support. For example, This is the example of lower Schrick, what the lower Schrick functor is doing. If y is a point f lower Schrick of f is gamma c xf, sections with compact support. And if x to y is a closed set, then f lower Schrick is f lower star. You don't have to, I mean, everything is going to be proper. Every section. Support of S is always a closed set. And what we want is that the map from there to Y should be proper. But if the other interesting case is when X is open. Then this is called as this is a subsheaf, which is called as extension by 0, extension of f by 0. Yeah, extension by 0, I should just. Yeah, you can say extension of f by 0. Basically, what is happening is if it's an open set, then we are just saying that we are looking at only those sections which can be automatically viewed as sections over the bigger open set, because their support is closed in the bigger open set itself. So you can automatically view them as a section over a bigger open set. So that is what that f lower Schrick construction is. This being the highlight, because it's giving you the sections with compact support, and that is what is going to come in handy in describing, in relating it to Poincaré duality. But a quick remark here is that while f lower Schrick has been defined at the sheaf level, individual objects, f upper Schrick is not really defined like that. F upper Schrick is defined only at the derived category. So while f lower Schrick is defined for individual sheaves, this is not so for f upper Schrick is only defined or derived at the derived, or derived category. There are some exceptions. So for example, one exception is for an open set. So that's a good news in this case. For f, or if you want, I can call it I, u to x open set. One can show that I Schrick, one can, the inverse image functor or restriction can be used for I Schrick, meaning the derived version. This is an exact functor, and its derived version will be in some sense itself, and that will actually work as I upper Schrick. And so what that means is, unlike the situation for schemes, in this case, the f upper Schrick localizes. You can actually calculate f over Schrick on an open subset. Replace x by an open set and then try to work it out, if it is convenient. Okay, so that ends my part 1. And now I'll start part 2, which is sort of a sketch proof of Grothendieck duality. So I won't. No, I didn't mention that. So yeah, that needs some argument. One can sort of give an argument, but right now I don't have the. One can give an explanation for why one should not expect f upper shriek to be defined at individual level. That's all I'm saying. One can give an argument, but I don't have that argument at the top of my head right now. F upper shriek is defined for complexes, yeah, at the level of complexes. So I will sketch a proof. I may or may not reach there today. I'll sketch a proof of the construction of the right-hand joint, at least when y is a point and k is a field. That is good enough for Poincaré duality. And there you will see that the way it's constructed in the derived category.
So, excuse me. So in the Grothendieck duality,
yeah.
So what is kx and ky there?
Sorry. So kx is sheaves whose sections over any open set is a k module. You can also view it as a module over the sheaf of rings given by the constant sheaf, which sometimes will denote it as k tilde x. So this is the sheaf of constant sections on x locally. I mean, constant sections mean for every open set, you look at functions from that open set to the discrete ring k, which are continuous. So this gives you a sheaf of constant function, constant set. This is what is called the constant sheaf. So on connected components, it's exactly the sheaf has sheaf assigns to the open set exactly k, nothing more. And for a union of connected components, you'll get that many copies of k. And you can also think of kx mod as sheaf of modules over this ring, this sheaf of rings. But just think of it as sheaf of abelian groups where every open set is a k module. And restriction maps are k linear, whatever you expect, standard properties.
Okay.
Sorry, quasi-coherent too? Yeah, no, this is in the topological setup, right? So I don't have any, I mean, there's no. Which modules? All kx modules. I am using all kx modules, yes. Yeah, I'm using all kx modules. Yeah. Okay, so this is sketch proof. But it'll take a little while before we get there. So I'll first mention a few basic things. These are there in standard textbooks. So I don't know how much, at what speed I should cover them. So I'll just mention some terms here. So let F be a sheaf of X modules. Okay, k is not really playing a role here. So let me just say sheaf of abelian groups, if you like. Now, okay, it's not really playing a role, but still let me keep it like this because I want to talk about injectives. So here are the 4 definitions. Then F is called injective. I guess you all know what this is. So that is the most basic one. And so that is if HOM into F is exact. Again, this is HOM over KX modules. Ask if Fx to Fu is onto for all u in X open. Soft, there's one more definition. If Fx, so instead of open, sorry, this Kx was somewhere here. Instead of open, you can confine yourself to closed, or maybe I'll put compact here, is onto for all K in X compact. This needs a little bit of explanation because typically when we talk about pre-sheaves or sheaves, we only assign sections to open sets. But in fact, you can do that for any set by taking a certain limit. So this is actually, maybe I should write it here. So these are sections defined over a neighborhood. So K contained in lambda, F of lambda. These are open. So take your compact set, find any open set which contains it, and take this family of open sets, and then this will be a directed system, and then take the limit over this directed system. And last definition is, which is sort of actually, in our case, it's almost, I mean, probably equivalent to the soft condition. And that is gamma C acyclic. So sections with compact support, it's acyclic for this functor if which I C X F is 0 for I greater than 0. This is just a derived functor of sections with compact support. So these are the definitions. Okay, the next thing I'll do is I'll very briefly mention why you can find such resolutions. So we will need resolutions which are injective or flask or soft or acyclic. At least the first three we'll definitely need in varying contexts. So I'll very quickly mention why they exist. Again, you can find them in standard texts. So part A. So injective resolutions exist because you can embed any F inside an injective sheaf. Injective in this category, if you like, the category of KX modules. So if for each X belongs to X, if EX is an injective K module, then the assignment U goes to direct product X belongs to X. Okay, so now I want to make a sheaf out of this. So what I'll do is that for every point I will put this, but I need to put some. So okay, so yeah, just EX. Defines. Sorry. Sorry. So thanks. And injective sheaf. When I say injective sheaf, I mean injective in that category. And so thus, every kx module admits an injective resolution. Again, it's a standard result found in many textbooks that injective sheaves are in fact flask. So there's a reason why we go in this order. Basically, these are larger and larger categories. So injective implies flask, implies soft, implies acyclic. So that's yeah. So that is basically what you do is if I is injective and if U inside X is open, then what you do is you look at I of X, then this is Hom AX into I. And then you look at I of U. You want to say this is surjective, but this will turn out to be Hom. So that is the J lower Schrieg construction there. So let me give this inclusion a name. I often need that. So let's call this J. And this is J lower Schrieg AU. And what we know is that J lower Schrieg KU is an open subset of KX. KX, actually, I should maybe put tilde here. I'm being a bit loose, sloppy here. But anyway, it's no point putting more declarations. Okay, I'll just put that. So that by definition of injectivity, this is an inclusion of sheaves. So this is basically sheaves. This is basically sections which are supported, sections whose support lies inside U, but it's closed in X. So this is extension by 0. So one can check that this is actually a subsheaf here. And then by definition of injectivity, this map is onto. So that shows that this map is onto. Sorry, this was B. Moreover, for any sheaf F, the sheaf U, you assign it to direct product of Fx, X belongs to U, is a flask sheaf. So in fact, there are other ways of obtaining a flask resolution. This being, the advantage here being that this is more canonical. The sheaf is a flask sheaf and containing F. One can give a natural map from F to this. And so this thus, this gives a canonical punctorial, if you like, resolution of a flask resolution. And this is called the Godma resolution. So this is useful because it's functorial. Next, we remark that Flask implies soft. So that's pretty much because you have f of x and you're interested in looking at f of k. But what is this? We said this is actually limit of over u lambda, f of u lambda. But the thing is, so these are open. But we already know that there are surjections like this, compatible with restriction maps. So this makes this a surjective system. And so the map to the limit will also be surjective. But what is interesting is some examples of soft resolutions. And this will bring us closer to Poincaré duality. So let's take X to be a differentiable manifold. I mean a C infinity manifold. Of dimension n. And look at EPX. This is the sheaf of infinity P forms. You can vary the coefficients. I mean, you can, sorry, not vary. You can have them coefficients in R or C. So C infinity functions in R or C. But anyway, it doesn't matter. So for the time being. So then E0. So that's the sheaf of C infinity functions. And then this one, and this D is the usual exterior derivative on every open set. And so on and so forth. ENX 0 is a soft resolution of the constant sheaf Rx. Okay, here R or C again. That depends on what coefficients you put here. Maybe I should not have. Okay, soft resolution of. Again, this is the constant sheaf. So these are constant sheaves. Sheaves which on open connected sets just assigns the value R or C. I mean, just assigns all the set of all real, the group of all real numbers or the field of all real numbers or complex numbers. So to see that this is a resolution, and we have to see that this is also soft. So to see that this is a resolution, we use the standard Poincaré lemma. So this is a resolution by Poincaré lemma, which tells you that locally in whatever star-like neighborhoods, if B of something is 0, it actually comes from a form of one lower degree. And the fact that it's soft is basically a partition of unity kind of argument. EIX is soft. So Yeah. So basically, so here I'll use, okay, this is a manifold, so certainly locally compact or normal. Sorry? No, I think it's not Flask because if I give you, I mean, it can be, you can have a, I mean, I can have a function on this which has a, which may not extend beyond a certain, beyond that. So it may be unbounded. So these are not Flask. Okay. Yeah, to check that they are soft. Yeah, so basically you'll have to take a section on a compact set. So let take S belonging to by definition it extends to Sx, by definition it extends to a section over an open set. Some open, but because these are manifolds and so they are locally compact, I can assume that this open neighborhood or I can use compact neighborhood. Sorry, not the same K. N containing K in its interior. I mean, you have a lot of flexibility. So I don't know if this is the right. I mean, all I want to do is I want to construct a C infinity function, which is one outside, one on N and, oh, sorry, one on K and 0 outside N. Phi from X to R, C infinity, such that phi restricted to K is 1 and phi restricted to X minus N is 0. And phi S extends. So just the usual partition of unity or whatever, this bomb function kind of thing. So this is so we have a soft resolution, which is more interesting because this will tell us what our cohomology we are measuring. So now we know that it's going to, if you calculate the cohomology with compact support of this constant sheaf, this soft resolution is telling you that you are actually computing the RAM cohomology. And the last bit is no, I didn't say that. Did I say that? No. No, I don't think so. No. You need to check it for compact sets. For a point. Yeah, I don't know. I see. Assuming paracompactness, I'm not sure. I don't know the answer offhand. Soft implies acyclic, so I think. So if you are familiar with, so this is soft, these soft sheaves are not used in algebraic geometry, but in algebraic geometry, we have use for Flask sheaves. But if you're familiar with how we prove Flask implies acyclic, then this is a very similar proof, except some technical modifications. Soft implies acyclic, essentially enough to show that for 0f, let me write, yeah. I guess I'm going a bit slow here. I hope it's okay. And then we'll come back to sketch proof of Poincaré worthier, but may not be today. I'm given this, then, okay, so maybe I'll just try to speed up a little bit here. So F1, F2, soft implies F3 is soft. And that sort of also will tell you that F2, gamma C F2 X F2 to gamma C X F3 is on 2. Okay. Yeah. Okay, why don't I try to just give a sketch proof? So the idea is, if I give you, okay, so first let's pretend that X is compact. If X is compact, see the obstruction to proving the problem in getting this surjective map is that even though we have a surjective map of sheaves, we know that the map at the level of sections is not surjective. Given a section over an open set here, or even over the whole set, we only have pre-images over an open cover. So assume X is compact, then you will have pre-images over an open cover. But since we assume locally compact space, you can replace those covers by open covers by compact neighborhoods, if you want, finitely many because X is compact. And then over the overlap, any two of those sections will agree here, but they may not agree here. So you are not able to glue them, but the difference goes to 0. So it comes from here. This is soft, so you can extend. You can extend from a compact set to the whole space. And so therefore, you can adjust the sections here. And since you can do this over finitely many open intersections, intersections of compact neighborhoods, you can in fact, given a section over the whole space, you can lift it. If X is compact. Because we wanted the overlapping overlaps, because we wanted to have finitely many compact sets where they intersect, I mean, compact neighborhoods which cover your compact space, and the intersections are compact, and then you can lift them. Now, if X is not compact, then your section still has compact support. So you can find you can cover it. You can cover the support of S by a slightly bigger, just like somewhere here we did, slightly bigger compact neighborhood which contains your support in its interior, and then once again you can lift the section on that compact neighborhood. You can lift it all the way here by our previous argument, because now it's supported only along a compact set. And you would like to extend it, but now notice that on the boundary, it may not be 0, what you have extended, what you have lifted, but the boundary is totally disjoint from the support. So on on that compact set with the boundary of that neighborhood you have chosen, bigger neighborhood of the support, the section is going to 0, and so you can lift it, you can extend it, and again adjust it. So I don't know, I'll just go a bit fast over this, sorry about that. It's not hard to prove, and that will show that you can always lift, and that will also show immediately that F3 is soft, because you just restrict to compact sets. Given a section over a compact set, you can extend it. You look at the, we already showed that you can lift it, and here you can in F2 you can lift it to the whole space and look at its image. That will give you a lift. So you can also show F3 is soft. And once you have these two properties, then it's enough. That will imply that soft is acyclic, because that will show that H1 vanishes. Once you know H1 vanishes and all three are soft, then just by induction, you will get higher HIs also vanish. So, sorry, I'll just go over a little fast. So how much time do I have? Is it over? Time is over? Okay. Maybe I'll do the sketch proof next time. It's just a 5-10 minute job, but okay. I mean, I don't know, maybe people are exhausted now. I'll just stop here. One last definition maybe I'll make, just 1 minute, which is finite dimension. So we'll say a space is finite dimensional, finite cohomological dimension. That is what comes up in the statement of Poincaré over there. So we'll say a space is finite dimensional if this functor gamma with section support functor has all the cohomologies vanishing after a fixed number. So if there exists a number n, maybe I'll just write this, sorry, just write this here. So this is homologically. Yes. Or if you want of dimension n, if so that will be our definition. And we'll see next time that, for example, an n-dimensional manifold will have dimension n, exactly n. You can see that it has dimension at least n, because here's a resolution of length n. And using this resolution, you will have, by integration here you will have a non-trivial cohomology in the nth spot. But we will also see that it has dimension at most n. And then we are ready to give a quick proof of Poincaré over here with all this. At least when y is a point. Then after that, I'll move on to Grothendieck duality, and I'll mention how it is slightly different from here. I have already sort of hinted. The problem is the adjoint functor is not local, and so we'll have to do something else to get the right functor. Okay, so I'll stop here.
So are there any questions for the speaker?
No, it's not generalization. It's just the, I said it's an analog. It's Verdier duality is a generalization of Poincaré, and it's generalization in the sense that it's an analog for singular spaces. See, that is what Grothendieck duality was doing for Serre duality. I mean, in the sense that Serre's original statement, classical duality, is for smooth varieties. Serre also had something probably for normal varieties, and Grothendieck generalized it to pretty much not just any variety, but any map of schemes. So in that sense, this is a similar generalization of Poincaré duality for any map of spaces, but some conditions like locally compact, finite dimensional. So no assumptions, no orientability assumptions, everything. I mean, all that comes built into it. So we'll see that f upper shriek of kx will be rx, r tilde x will be the orientation sheaf, and all those things I'll mention next time. Why it is generalizing Poincaré duality. No, they are formally similar. That's all. Because the setup is totally different. Here, this is locally compact Hausdorff spaces. There it is Noetherian schemes. So the setups are totally different, but they are formally similar statements. What are similar? Yeah, I mean, because they are similar, so if you know what is happening here, maybe you also can guess what is happening here. You can look at the analogous construction here, and so on and so forth. I mean, essentially, it is more useful when things are singular. So that is probably where you see the connection. Yeah.
Okay, are there other questions? If not, let's thank Suresh once more.